Hello and welcome back to episode E. This is the fourth video of my series on polynomials. Today we're going to be looking at quadratics. So the basic quadratic equation is of the form ax squared plus bx plus c equals 0. And the first step when solving any quadratic is to divide through by a. X squared, which just gives, I'm just going to write this on the same equation, divide through by a, which just allows the a's here to cancel, and 0 divided by any number will stay being equal to 0, so we may as well just ignore this a. So I'm going to rub it out. And I'm going to rub out these terms. So now that we have it in this form, I'm sure some of you may already know how to derive the quadratic formula by completing the square. If you've never done this, I recommend you give it a go, and I'm going to pause the video and I'm going to have a quick drink while you do that. So, now that you've unpaused the video, today I will show you a graphical method of how to derive the quadratic equation. Now that we've got an x squared coefficient of 1, it makes things a lot easier, and we can draw the graph. So, this will give us a quadratic. If I didn't rub out my graph, that'd be very helpful. A quadratic of this form, where the minimum is some distance off the y-axis. And this is a normal positive quadratic. I could show a negative quadratic, but I don't see the point at the moment. What I feel it would be nice to have is if we had x squared plus some a equal to 0. Because then we could just have x squared is equal to minus a, and then x is equal to plus or minus the square root of minus a. Now, it doesn't really matter if a is positive or negative because we're allowing complex solutions. And anything x squared plus a would be of the form here, where the minimum, I've drawn this terribly, it would be on the y-axis. And in order to find the translation that we need to perform in the x-axis to get our original equation onto x squared plus a, we have to find the minimum here and find the minimum here, and then find the difference between them. So, the minimum value on the axis will obviously be 0, and the minimum value over here we can work out by finding the derivative of the original equation and putting it equal to 0. Because when the derivative of a quadratic function is equal to 0, that is where the gradient is 0, and therefore that's where the minimum is. So, we have our f of x is equal to x squared plus b over ax plus c over a. Therefore, f dash of x, which is just the derivative of x, is equal to 2x plus b over a. We can get rid of, if you've never seen this before, I'm using Leibniz notation, which is just multiplying by the power and then taking 1 from the power. So now this is x to the 1 here. This last term disappears because it would be multiplied by x to the 0, which is just multiplied by 1. And if you multiply this by 0, anything multiplied by 0 gives 0, so this whole thing leaves the equation. So we have 2x plus b over a, and let's put it equal to 0 because we want the minimum, and solve. So I have 2x is equal to minus b over a, and then x is equal to minus b over 2a. Good, so now we have the minimum of the function, and we have the distance from the y-axis. So the original minimum here is a distance of minus b over 2a from the y-axis. The way we're going to use this in our equation is we're going to write x minus b over 2a in replacement of every x in the original equation. So we're going to square this plus b over a times x minus b over 2a plus c over a equals 0. And this will give us x squared minus 2xb over 2a plus b squared over 4a squared plus bx over a minus 2b squared over 4a squared plus c over a, and that will also be equal to 0. Now, we can cancel these 2's, and then we have a bx here and a bx here with opposite signs, so we can just get rid of those two things. And what this leaves us with is x squared plus 4ac minus b squared over 4a squared is equal to 0. Now to solve, we just go into our autopilot and we get b squared minus 4ac over 4a squared. This is looking promising. And then we square root, we have x equals the square root plus or minus the square root of b squared minus 4ac over 4a squared. Now some of you may have noticed that the square root of 4a squared, I'm going to draw that 2 again because it's an abomination, is equal to just 2a. I'm writing it like this because it will make more sense with the next step. To undo the shift, we simply add minus b over 2a to the right-hand side, or we add it to the right-hand side. So we have x equals minus b over 2a plus or minus the square root of b squared minus 4ac over 4a squared, which can also be written in the formula I'm sure you're more used to of minus b plus minus the square root of b squared minus 4ac all over 2a. So that's your quadratic formula derived. Before I finish this video, I'm going to talk a bit more about what we call the discriminant, which is just your b squared minus 4ac. What this does is it tells you how many solutions there will be, or it tells you how many real solutions there will be and what kind of solutions there will be. So first of all, if b squared minus 4ac is positive, there will be 2 real solutions. Secondly, if b squared minus 4ac is equal to 0, then this square root is equal to 0, and so we're just left with x is equal to minus b over 2a. So we only have one solution, which is a repeated solution, which would look like this. Where it does touch the x-axis at one point, but it doesn't cross. The third thing we have to think about is if b squared minus 4ac is negative. If b squared minus 4ac is negative, then we have a negative thing inside the square root sign, and that will give us a complex solution. It will give us 2 complex solutions, and what those solutions will be, they'll be conjugate pairs. So what that means is if a plus bi is one of the solutions, the other solution will be the conjugate of that solution. That's what this line over the top will mean. I will attach a symbol sheet to this video. So the other solution will be simply a minus bi. And that's our conjugate pair. Anyway, thank you very much for attending episode E of my series on polynomials, and I will see you all next time.